Hello, Computer Science 221 students. Welcome to the lesson about strong mathematical induction and relations. Strong mathematical induction is very similar to ordinary induction we studied last time. We were studying about ordinary induction. Today, we're gonna learn new technique called strong induction. And trust me, they are very similar. They differ by a little, but they're very similar. So as a review from last time, let me quickly show you what we did from ordinary induction. In this slide here, everyone, you don't have to copy it down on your notes, but I'm just going to briefly explain the clear difference between ordinary induction versus strong induction. In the ordinary induction, we used two steps to prove the statement. For example, base case. We prove the first domino case by checking whether the predicate is true when we plug the first integer. So this knocking down the first domino was the base case in the ordinary induction. Now, using the fact that the first domino is knocked down, the second inductive step was to choose arbitrary integer k and assume that this kth domino was already knocked down. We just have to show that using the kth domino to knock down the next domino. That was all we've done last time. And using the fact that P of k is true, we show the next domino is also true. So that's about ordinary induction. Now, the clear difference between strong induction and ordinary induction is that proving base case might be a little bit different. For example, look at this. Before everyone, the ordinary induction base case, we only have to check one. In other words, we only had to show one domino knocking down. But for strong induction case, sometimes you only have to show one domino to knock down. Sometimes you might have to prove multiple base case. For instance, not just one domino at the beginning. You might have to prove first two dominoes or first three dominoes and so on, depending on the situation. So one of the clear difference between ordinary induction base case and strong induction base case is that you may need to prove the truthiness of first few dominoes. P of A plus 1 up to P of B, And the second difference between strong induction and ordinary induction is the inductive step. In the case of ordinary induction, we know that the kth domino is knocked down. We were able to show that this kth domino has enough power to knock down the next domino. That was about ordinary induction, do you understand? But in the case of strong induction, our kth domino does not have power to knock down the next domino. In other words, suppose we have a statement P of k plus 1, which is so heavy, for example, it's so heavy to knock down, so that using one P of k domino to knock down P of k plus 1 is impossible. Let's say we need the truth of all dominoes before k plus 1 domino. As the dominoes knock down, we have more power as a momentum to knock down the last domino, which is k plus 1. So the idea of inductive step in strong induction is that we need truthiness of P of 1, P of 2, and so on up to, we need to assume P of 1, P of 2, up to P of k, all statements are true, so that this momentum with all the powers that we collected can knock down the P of k plus 1. That's the idea of strong induction. We're going to see two examples where P of k plus 1 is so heavy so that one domino cannot knock down the next domino. We need the power from previous dominoes. We're going to get to this, okay? But for this slide only, make sure you understand the base case. You may need to prove multiple statements at the beginning. For the inductive step, you have to assume all statements P of A plus 1 up to P of k, all statements are true in order to knock down the next one. By the way, everyone, because we already know from base case P of 1 or P of A here, P of A plus 1 up to P of B are all true, we don't have to repeat writing P of A plus 1 in inductive step. We just have to assume all statements up to k, where k is greater than or equal to b, are true. Assume P of B plus 1 up to P of k are all true. Now, using this strong power and momentum to knock down P of k plus 1. That's our goal in inductive step. So in summary, everyone, if you understand how to do some ordinary induction proof, you technically know how to do strong induction proof. They are very similar, but for the base case, you may have to prove multiple statements sometimes. Inductive step, instead of assuming just P of k domino is true, we have to assume all statements greater than or equal to P of B are true. Then show P of k plus 1 is also true. This step is exactly the same. Okay, so as a summary, let's write down something on the next slide. You can continue writing the notes. For both cases, we're proving a universal statement like this. For all integers n greater than or equal to a, the predicate P of n. The base case for ordinary induction, you just have to show the first domino is knocked down. That is, P of A is true. For the base case for the strong induction, you may need to check multiple statements starting from P of A. The inductive step for ordinary induction, assume the kth domino is true, knock down the next one. Assume P of k is true for some integer k greater than or equal to a. Now, show that the next domino is true. The inductive step for strong induction, we need to assume all statements starting from P of b up to P of k. So, assume P of b and P of b plus 1 up to P of k all are true for some integer k greater than or equal to b. Same thing as before. Using this power and momentum, show P of k plus 1 is also true. Okay, here's the summary of the difference between ordinary induction and strong induction. I think we're ready to tackle 2 examples about strong induction. Here is a little note before we do the example. It's quite obvious. Strong induction can prove any statements that can be proved with ordinary induction because it's so strong, or vice versa. However, we're going to do 2 examples today. Those examples require this kind of argument form to prove the statement. Okay, let's consider first example about sequences. Here's the first example about sequences. And let me tell you the answer. We want to use strong induction for this one. Do you know why? Because our sequence AK, which means 6 times AK minus 1 minus 5 times AK minus 2, the general term, which is written as recursive formula, depend on the result of the previous 2 terms, AK minus 1, AK minus 2. This is the reason why we need A0 equal to 0, A1 equal to 4 to get the next term in the sequence. The next term in the sequence depends on the previous 2 terms. Do you understand? Did you just hear what I said? The next sequence, A2, depends on the previous 2 terms, A0 and A1. Do you know what this means? It means we need truthness of the first 2 terms. That means our base case cannot be just 1. Our base case must be checking two P of 0 statement, truth of P of 1 statement. Both have to be true in order to talk about the later terms. So now we have to use strong induction. Let P of n be the statement smiley face, where this is our smiley face. We prove the statement by using strong mathematical induction. We prove P of n for all integers n greater than or equal to 0 using strong induction. Once again, we're using strong induction because our sequence need the truthness of first two terms. In the previous lecture, if you remember, we proved similar statement using sequences. However, the only difference between this example and then our new example today is that this recursive formula, AK, depends only on the previous term, one term, whereas our today's new example requires two previous terms. You see, we need AK minus 1, AK minus 2, the two previous terms, in order to get AK. So, as a base case, let's check the following: A0 equal to 0, A1 equal to 4 for the following formula here. Consider P of 0 and P of 1. We're going to prove the left-hand side of P of 0, right-hand side of P of 0, and see if they're equal to each other. We're going to prove left-hand side of P of 1, right-hand side of P of 1, and see if they're equal to each other. We're going to use this formula, an equal to 5 to the n minus 1, but we're using the sequence from above. Left-hand side of P of 0 is A0, which means 0. Right-hand side of P of 0 is 5 to the power of 0 minus 1. And surely it's 1 minus 1, which is 0. This shows our P of 0 is true. Let's do the same thing for P of 1. Once again, the left-hand side of P of 1, right-hand side P of 1, they're equal to each other. Therefore, P of 1 is also true. So these two things show that the base case of my strong induction must be true. The inductive hypothesis in strong induction, we have to assume P of 1, P of 2, up to P of k are all true for some k greater than or equal to 1. Assume these statements are all true, where k is some arbitrarily chosen integer greater than or equal to 1. Here's what we want to do. We want to show P of k plus 1 is also true, just like the ordinary induction. Showing P of k plus 1 is true, it means we want to show a k plus 1 equals 5 to the power of k plus 1 minus 1. So left-hand side is a k plus 1, right-hand side is 5 to the power of k plus 1 minus 1. Okay, we're going to start from the left-hand side and show the right-hand side. The left-hand side of this equation is ak plus 1. For ak plus 1, we follow this recursive formula. Ak plus 1 equals 6 times ak minus 5 times ak minus 1, because we have k plus 1. And we must satisfy that k must be greater than or equal to 2, in which case it's true. And of course, our k is currently greater than or equal to 1. Therefore, k plus 1 must be greater than or equal to 2. Now, here is the important part of the proof. We need the truthness of ak and ak minus 1. Our goal is to somehow change ak in terms of this kind of looking function, but we need the truthness of ak, that's first truthness, and also we need the truthness of ak minus 1. Since we need two dominoes to knock down the next domino, this is the reason why we need a strong induction instead of having just one domino knocking down the k plus 1, we need at least 2 dominoes knocking down the k plus 1. So that's why we have to assume the preceding dominoes that are true. And indeed, we can use AK, we can change AK minus 1 in terms of 5 to the power of k, 5 to the power of k minus 1, because our inductive hypothesis says assume p of k and then the preceding p of k minus 1 are all true. It's very, very important. Because we're assuming all the statements are true, we can now go ahead and switch this AK in terms of formula, AK minus 1 in terms of formula on the right-hand side. 6 times AK minus 5 times AK minus 1. So 6 times AK means, go back to our formula, AK means 5 to the power of k minus 1. Now, AK minus 1 means 5 to the power of k minus 1 minus 1. And the reason from this step to this step is called inductive hypothesis. Okay, now let's do some math, basically simplifying this expression using algebra. First, I'm going to feed chicken 6 times this and 6 times this. And then same thing for the other factor. We get, look, we have 5 times by 5 to the power of k minus 1. This k minus 1 becomes just k because we have same base 5. And finally, negative 5 times negative 1 becomes positive 5. And let's collect the like terms. 6 5k minus just 1 5k becomes 5 times 5 to the power of k. And then negative 6 plus 5 becomes just minus 1. Okay, wait a minute. We have 5 to the power of 1 times 5k. It's equivalent to what we want. 5 to the power of k plus 1. So now we have left-hand side of p of k plus 1 equals the right-hand side of p of k plus 1. We've successfully proved that p of k plus 1 is now knocked down. So by strong mathematical induction, we finally proved that the statement p of n is true for all integers n greater than or equal to 0. Alright, this is the end of the example. And here's a little tip about strong induction. Usually, strong induction is used when we have recursive sequences like this, just like before. So when we talk about recursive sequences, we need at least 1 or 2 information so that we can get the next later terms. So using these first 2 terms, we can get the next later terms, say AK, where it's the summation of the previous 2 terms. So the later term depends on the previous 2 terms. When this happens, then we need multiple base case. What does that mean? It means we need strong induction. Another famous situation where we need strong induction is when the inductive step need the truth of all predicates, where the integer I runs from some number b up to k. For example, we assumed all statements greater than or equal to 1, which means p of 1, sorry. This is so strong so that we were able to change ak to this formula because they are true. Ak minus 1 became this formula because we assume this is true. So when we need inductive step requires multiple truthness, then we have to use strong induction. Okay, let's try the last example. This is something to do with the prime numbers. In case some people forget about the definition of prime numbers and composite numbers formally with the quantifiers, I'm going to give it to you right now. Please take a look closely. We're going to use those definitions. In case some people forget about the definition of prime number, composite number, here you go. I've copied and pasted from week 3-1 lecture slide. Basically, I want you to focus on this composite definition. If you can represent n in terms of r times by s, and if you have this situation, r is in between this and this, then we can call that number n to be a composite. Okay. Hang on to this definition. We're going to use this almost the end, so please keep that in mind. For now, we're going to prove the following statement. The first few sentences will be easy to follow. Any integer greater than 1 is divisible by a prime number. For example, if you give me 4, 4 is divisible by 2. So surely 2 divides 4, right? Even if you give me prime number 7. Surely prime number, the factorization of prime number is 1 and itself. Surely 7 divides 7, right? So it's indeed true, any integer greater than 1 is divisible by a prime number. That's true. But I want to prove using clear and rigorous proof using induction. Let's call this whole statement to be smiley face. Then our predicate P of n be the statement, the smiley face. We're going to prove the smiley face statement for all integers n greater than 1. Do you know what this means? N greater than or equal to 2. That's what it means. Because n is strictly greater than 1 means we have to count the integer from 2. We prove this statement using strong mathematical induction. The base case in this case, we don't need to check all multiple statements at the beginning. One statement is okay this time because it's not like a sequence. However, keep that in mind. In the inductive step, we need the truth of all statements up to k. And I'm going to show you why. Okay? So for now, let's check the first domino when n is equal to 2. Remember, n must be starting from 2. You know that, right? Because n must be strictly greater than 1. Then our left-hand side is just 2, right? And then the right-hand side is 2 is divisible by a prime number, and it's true. So here's my predicate of P of 2. What do you think, everyone? Do you think this predicate is true or false? 2 is divisible by a prime number. If you said it's true, then you're correct, because the number 2 itself is a prime number. Inductive hypothesis is that we're going to assume P of 2, P of 3, up to P of k are all true for some integer k. Now, our goal is to show that P of k plus 1 is also true. Do you know what this means? It means the integer k plus 1 is also divisible by a prime number. We want to show that that's true. But by the way, everyone, look at the integer k plus 1. K plus 1 is an integer, right? It could be prime number. It could be composite. It's one or the other, right? Everyone, we don't know whether k plus 1 is a prime number or composite. So we need to consider two cases. Treat k plus 1 as prime number. That's case 1. Case 2, treat k plus 1 as composite number and then show that the statement is true. Okay, first case is easy, really easy, because if we assume k plus 1 is a prime number, it's nothing more than the base case where k plus 1 is a prime number, so k plus 1 is divisible by itself, which is a prime number. If you assume k plus 1 is prime, then surely the predicate P of k plus 1 is true. Thank you, everyone. Case 1 is done. P of k plus 1 is true because k plus 1 is divisible by itself if we assume k plus 1 is prime. So the statement is true. Now, case 2. How about k plus 1 is a composite number? Everyone, assume k plus 1 is composite. What does that mean? It means if k plus 1 can be written as some number r times by s, where r must be greater than 1, less than the number k plus 1, and same for the s. So I'm just going to rewrite the whole statement here for the definition of composite. k plus 1 can be written as the product of two numbers, say product of two integers, where r and s are in between this. But everyone, look at the inequality carefully. You know that r and s are integers, right? But r greater than 1 means you cannot have r being 1. It has to be at least r equal to 2. That's the lower bound of this inequality. Look, r must be strictly less than k plus 1. It means r must be less than or equal to k as an integer. Same for s. You know, you guys might think that changing from here to here, you guys might feel that it's not so important. But you know, it will be very important. Do you know why? Because r, the truth of p of r greater than or equal to 2, less than or equal to k, is so important because of our assumption the integer r is in between p of 2, p of 3, and p of k. We are assuming all statements p of 2, p of 3 up to p of k are true. In order for us to use these statements in the inductive step here, we need to change the inequality in terms of 2 and k. And knowing that r is in between 2 and k will help you prove the statement using the strong induction, our assumption here. Okay, listen carefully, everyone. Since the integer here, r, is greater than or equal to 2, less than or equal to k, we are 100% sure that r is divisible by a prime number. Let's say that particular prime number is p. Do you know why this statement is true? Because look at this. For any integer in between 2 and k, we're assuming 2 is divisible by a prime number, 3 is divisible by a prime number, up to k is divisible by a prime number. And since r is in between 2 and k, we're 100% sure that r is divisible by a prime number, let's say p, by the inductive hypothesis. Write this down. Okay, look at this statement carefully. R is divisible by a prime number p. We can change this as a mathematical statement, like p divides r, like this. This statement means p divides r. And everyone, I have a really great news. Look at this, our equation carefully. K plus 1 is equal to r times by s. I'm sure you guys understand that r times by s means k plus 1 can be written as a multiple of r because s is an integer. If k plus 1 can be written as a multiple of r, this means r divides k plus 1. On one hand, we have p divides r. On the other hand, we have r divides k plus 1. I have a feeling that we can use the transitivity property p divides r and r divides k plus 1 combined together, so it becomes p divides k plus 1 using the transitivity property. Did you guys realize that we are done with the proof? Because our goal was to show that k plus 1 is divisible by a prime number. What did we do here? We just proved that p divides k plus 1. What does that mean? K plus 1 is divisible by a prime number p. Therefore, p of k plus 1 is true. And congratulations, this is the end of the whole proof. By strong mathematical induction, p of n is true for all integers n greater than 1. Thank you. This is the end of all induction topics. Let's have some break, everyone. See you soon. Part number 2, relations. As a warm-up, please consider the set A, which is 0, 1, 2. B has elements 1, 2, 3. Let's quickly find A cross B, which is the order pair 0, 1 is one of them, 0, 2 is another one, and so on. Okay, let's quickly write down this Cartesian product. These are all the elements belong to the Cartesian product A cross B. Here's the question. Consider all the elements in A cross B above. Find all ordered pairs satisfying the first coordinate is less than the y coordinate. Well, if I see the first element here, 0 is less than 1. So surely 0, 1, this element satisfies this condition over here. Same as this one, same as that one. However, look at this 1, 1. 1, 1 does not satisfy this inequality because x must be strictly less than y. Therefore, 1, 1 is out of the option. 1, 2 is okay, 1, 3 is okay, 2, 1 is not okay, 2, 2 is not okay, but 2, 3 is okay. So how many elements we have so far? There are a total of 6 elements that satisfy this inequality. So out of these 9 elements, only 6 elements satisfy this relation here. Here's the conclusion. We say x coordinate in A is related to the y coordinate in B if and only if x is less than y. The notation for this English sentence, we use this in mathematics. Did you notice this? X is related to y. We write it as xry, but of course, I prefer to write x and y closer to the r. This is the notation. So in this case, x is related to y if and only if x is less than y. So if you understand this notation, let's go back to our elements that satisfy this condition over here. We can write it as 0 is related to 1, 0 is related to 2, and so on, because they satisfy this condition over here. Another way of writing this kind of notation is that you see our happy smiley face elements. These elements belong to R. So R is a set containing these 6 elements. Did you notice that R is a subset of the Cartesian product A cross B? Okay, that's the end of the warm-up. I hope you remember this warm-up question and then the notation for relation, okay? If you don't, please repeat the video as many as you need to understand this process. If you do understand this process, let's move on to the definition. We say x is related to y. However, one thing that I want you to remember is that x comes from A, y comes from B, okay? If and only if this order pair belongs to R. Please note, A is called the domain of the relation R, and then B is called the codomain of R. It's not the range, okay? Range is the subset of the codomain. I know in high school we are more familiar with the term range, okay? But codomain is more bigger than the range. Range is a subset of the codomain, okay? If you have taken matrix algebra, then you probably understand what I mean by that. The negation of this one is x is not related to y if and only if xy does not belong to R. Please take your time to understand this definition. If you are 100% happy, let's move on to the example. Actually, everyone, I was planning to go to example right away, but in case someone who is still confused with codomain thing instead range, I will explain one more time. Could you think about a parabola? And let's call this function is domain is all real number, right? The domain is all real number to the range. Well, we don't know the range yet, but let's have this kind of function definition from real number to real number. What is a range in this case? The range of f is actually, it's not going to be all real number, do you understand? It's actually, I'm running out of space. Did you notice that the range is actually smaller than the whole real line, right? So that's why the range is actually subset of the codomain R. We should not say range is always equal to the R, okay? All right, move on to the example. Here's the first example. Define a relation E maps from set of integers to set of integers such that for all m comma n in z cross z, m is related to the n if and only if m minus n is even. At the first time, if you read this, you might say, what the heck is going on? But if you see the example over here, you probably will understand. 4e0 is same as saying that 4 minus 0 is even. Is it true or false? If you said true, then you're correct. 4 take away 0 is, of course, it's even. How about this? Is 5e2 even? No. So in other words, 5e is not related to 2. Okay. Does this make sense, everyone? The question is this. The question is, if n is an odd integer, then ne1 means n is related to 1. We have to show that this is true, okay? To show that ne1 is true is that we have to show n minus 1 is even number. That's all we have to do. And then we know the assumption here is that n has to be odd integer. In other words, remember, n is equal to 2k plus 1. Okay, that's how you start the problem. Let's write the proof. Suppose n is an odd integer, then you know n can be written as 2k plus 1 for some integer k. That's our introduction sentence. The rest is actually pretty easy. We have to show ne1. In other words, we have to show n take away 1 is even number. Did you notice that n take away 1 is a 2k, but 2k is what? It's an even number. Therefore, this n comma 1 belongs to E. That's the end of the proof. Before we move on, everyone, do you remember inverse relations? When we talk about inverse relation, or whenever you hear the word inverse, you switch what and what? You switch x and y coordinate, right? That's what we're going to do, the inverse relation. Suppose R is a relation from A to B. Define the inverse relation R inverse from B to A by, switch x and y. X comma y is switched, so we now have y comma x in B cross A such that xy belongs to R. So collect all the elements in R and then switch their coordinates positions. You might prefer writing this way though. For all x in A and y in B, y comma x is in R inverse if and only if x comma y is in R. Basically same as what we just talked about here, Last example. Suppose set A contains 2, 3, 4, set B contains 2, 6, 8, and define the relation from A to B by, for all x, y in A cross B, we have x is related to y if and only if x divides the second coordinate. Oh, I see that 2 divides 2 clearly, okay? 2 divides 6, 2 divides 8. So let's find out the set of all elements in R. So clearly, the order pair 2, 2 belongs to R. Unfortunately, 3 does not divide 2, okay? 3 does not divide 8. So the only order pair that we can take is 3, 6. 4 doesn't divide 2. 4 doesn't divide 6. But 4 divides 8. Hence, we have total of 5 elements in R. R inverse is basically switch their position, the X and Y. Okay, you switch this, you get 6,2. You switch this, you get 6,3, and so on. Okay. The last thing I want to do is draw arrow diagrams for R and R inverse. You know, R is going from A to B, okay? A is the domain, B is the codomain. Do you remember? As a diagram, A looks like a circular, set, and then containing the elements 2, 3, and 4. Okay, everyone. We know R has 2 maps to 2, 2 maps to 6, 2 maps to 8. Okay, and then 3 maps to 6, and then 4 maps to 8. Congratulations. This is the arrow diagram for R. Let's draw the R inverse quickly. It's going from B to A. Looks like 2 maps to 2 itself, and that's the only one starting from here. 6 maps to 2, 8 maps to 2, and then 6 maps to 3, and 8 maps to 4. Okay, everyone. This is the end of today's lecture. Next week, we're going to talk more about relations, functions, and sets, as well as the project. Have a great day.